This evening is it's a particular pleasure you've met or seen Colin just a few moments ago, but to tell you just a little bit about him. Just to repeat that he is the director of this Advanced Space Concept Laboratory at the University of Strathclyde, which has grown and grown and is now a very significant operation. His own unit is 30 people strong. Most of these are research students and postdoctoral researchers, but also include lecturers. It's an advanced space concept laboratory, which deals with technologies and new uses of space technology. And in that same grouping, we have a design and manufacture unit. I have a small interest in this because I was the principal of the University of Strathclyde. Design and manufacture unit that actually designs space mechatronic devices, and that's another technology laboratory which deals with space robotics, etc., etc. And that is sponsored to a very large extent by Chinese sources of funding. Not insignificant these days. And then there's a Centre for Future Aerospace Transport Systems, which is another 12 people. So this is a big grouping of scientists and engineers who are devoted to this work. And this evening, Colin is not going to talk about the technicalities of these engineering aspects. He will mention that, of course, but really what he's doing is talking about the impact of entropy and energy and human enterprise. So it's a sociological, if you like, if I've got it right, assessment of the impact of this process of thinking about the use of energy and entropy, which is a very interesting concept. So over to you, Colin, to make everything crystal clear. Thank you.
Professor Arbuthnot, ladies and gentlemen, good evening. I'm both delighted and honoured to receive the 2012 Royal Society of Edinburgh Lord Kelvin Medal this evening. My association with the Royal Society of Edinburgh actually dates back to 1988, when I was the Society's Robert Cormack Research Fellow. And I'm truly indebted to the Society for providing me with that initial opportunity to pursue a programme of curiosity-driven research, and also the recognition of what that programme of research has achieved. Now, in my lecture this evening, I propose to consider three ideas. First, that the human enterprise is a catalyst through which dead matter is organised into conscious life. That its successes have been in transcending rather than recoiling from environmental boundaries, and that the human enterprise can be a persistent, self-organising phenomena that has the potential to prosper into the deep future. So before we consider the future, let's first consider the distant past. It's now known that not long after the Earth formed and cooled, that dead matter got organised. Atoms of carbon and hydrogen and oxygen and nitrogen arranged themselves into simple patterns embedded in organic molecules. And later, after exploring innumerable dead ends, these organic molecules organised into long chains that could manufacture copies of themselves. Now, this was no mean feat for dead matter. The enterprise of replication could both store and transmit information, accelerating organisation. Much later, simple bacterial life emerged, leading to chemical disequilibrium in the Earth's atmosphere via the production of oxygen through photosynthesis. Okay, so dead matter was becoming organised and was changing the Earth, indeed polluting the early atmosphere with reactive oxygen as a byproduct from simple metabolisms. And yet this wonderful process of self-organisation, it seems to contradict the idea that entropy and disorder can only increase. But of course the Earth isn't a closed system. It's a truly vast heat engine, receiving hot photons from the sun and radiating cool photons to the heat sink of cold space. Thermodynamic processes due to evolution of organic biology are therefore noise in comparison to this colossal entropy engine. So Lord Kelvin's second law is quite safe. Long after this initial phase of self-organisation, the dead Earth itself achieved consciousness, not as Lovelock's Gaia, but as thinking, replicating humans. What were once dead atoms of carbon and hydrogen and oxygen and nitrogen self-organised to such an extraordinary degree that they literally began to walk the Earth. But of course, what was truly impressive was that the humans got organised. Through mimicking then language and eventually the imprint of writing, ideas could be stored and transmitted to others. Each new generation of replicating humans could avoid the dead ends of the past and learn from their predecessors while adding their own thoughts to the steady accumulation of knowledge and ideas. And these ideas were key. Again, until the relatively recent past, the unthinking Earth could only manipulate atoms such as carbon and hydrogen and oxygen and nitrogen through organic biology. But through the emergence of thinking humans, flows of inorganic materials such as metals began to be organised in a spiral of growing complexity. And in this new phase of self-organisations, it was humans themselves began to manipulate dead matter using energy to imprint their ideas on the world. And of course, these ideas were no mere idle philosophy. Soon ideas began to change the world, not to devastate it, but to give it utility. First, the reorganisation of aspects of nature through agriculture and the growing societal complexity of the Neolithic Revolution, and then the real awakening from millennia of Malthusian stagnation through the Industrial Revolution. Now, whether due to the far-reaching ideas of the Scottish Enlightenment or the innovations of pioneers such as James Watt, it was realised that the future could be radically different from the past. Importantly, it was through the Industrial Revolution that the human enterprise escaped from the photosynthetic limit of diffuse energy from biomass such as wood, which until then had severely constrained economic growth and human development. An early environmental boundary was transcended through the transition from wood to coal. The human enterprise had at its disposal compact means of delivering and consuming energy that set it aside entirely from previous generations. In fact, the end of the wood-burning era in Britain was precipitated by a national energy crisis in the early 17th century, in effect, peak wood. Now, wood is a diffuse energy source, and it required significant human labour to gather and to use. So, as practical resource limits were reached in the neighbourhood of population centres, transportable, energy-dense coal slowly became the fuel of choice for warmth and for emerging industries. In fact, such was the shortage of wood in central Scotland during the reign of King James VI, it was quipped, if Judas had repented in the king's native land, Scotland, he would have been hard put to find a tree in which to hang himself. So, the growing use of coal helped end this Elizabethan energy crisis and ultimately allowed an escape from the Malthusian trap of medieval subsistence. However, while the growing use of coal in the Elizabethan era paved the way for the Industrial Revolution, it was far from universally welcomed. Coal was seen as a dirty and polluting fuel, and at an echo of contemporary sustainability, some thinkers, such as agricultural writer Arthur Standish, advocated simply growing more trees to meet rising demand for energy, thus avoiding the use of coal at all costs. Writing in 1615, Standish claimed that there is no guarantee how long coal will last. And as an alternative, he proposed that there may be as much timber raised as will maintain the kingdom for all uses forever. Now, such an energy policy would no doubt have led to a sustainable wood-burning society based on renewable biomass, but it would never have led to the marvels of the Industrial Revolution. So thankfully, Standish was quietly ignored, and from then on, a potent mix of energy-dense fuel, later combined with radical Enlightenment-era thinking, allowed the human enterprise to use energy to imprint its ideas on the physical world on scales never seen before. And the continued availability of energy-dense fuels today is, of course, an overwhelmingly civilising and liberating influence. By replacing carbohydrate-fuelled human labour with hydrocarbon-fuelled machines, many of us have been freed from the land to think, innovate and create in a virtuous circle of prosperity. Indeed, in the late 19th century, the growing use of compact, coal-driven steam power enabled energy and labour costs to decouple for the first time in human history. Energy became cheap, while labour became expensive, and so prosperity, however unequally, began to grow. In fact, between 1830 and 1875 alone, per capita energy consumption in Britain more than doubled. And in a similar manner, between 1980 and 2010, China quietly lifted almost 700 million people out of poverty, again as per capita energy consumption more than doubled. This has been the single largest achievement in poverty alleviation in human history. Now, although it may seem surprising, it can be argued that the transition from wood to coal was both environmentally as well as ultimately socially progressive. As we noted earlier, in the 17th century, it was coal from the ground that began to save wood from the land. And in a similar manner, oil from the ground would ultimately save oil from whales in the late 19th century. Energy-dense punctiform fuels minimised their immediate environmental impact. And again, surprisingly, it can also be argued that the beginning of the transition from wood to coal during the Elizabethan era was also the beginning of the transition to a low-carbon economy. Once moisture is removed, wood has an effective carbon-to-hydrogen ratio of order 10 to 1, falling to 2 to 1 for coal. So once combusted, coal will deliver more energy and release less carbon than the equivalent mass of wood due to its more numerous carbon-to-hydrogen bonds. And this relative decarbonising of energy production from wood to coal continued much later through further transitions from coal to oil and then oil to methane. And as Jesse Ozzibel of the Rockefeller University points out, each new fuel has more hydrogen and less carbon than the last, leading to an increase in energy density and a reduction in carbon intensity. So the end point for these transitions is then methane, with 4 atoms of hydrogen for every atom of carbon, and an energy density approximately double that of coal. So per unit of energy produced, we've been moving out of carbon and into hydrogen for over 200 years. But these transitions were not due to climate. They arose simply because energy-dense fuels have greater utility and open up new ways of consuming energy, whether clean-burning methane to eliminate coal-burning urban smog, or energy-dense petroleum and kerosene to fuel internal combustion engines and aviation gas turbines. Now, it's also worth noting that Lord Kelvin took an interest in fuel burning in the late 19th century. However, his concern wasn't carbon, it was the depletion of free oxygen in the atmosphere during combustion. And due to a misunderstanding of the oxygen cycle at the time, Kelvin estimated that the atmosphere would be fully depleted of oxygen within 400 years. So how our concerns over fossil fuels have changed. As we consider these historical energy transitions, it's important to note that it's been slow and protracted affairs. And this is due to the time required to build out the infrastructure required to extract and to utilise new energy resources. For example, in terms of the share of primary energy production in the OECD nations, coal didn't overtake wood until about 1870, and its market share peaked in the early 1900s. Oil didn't then overtake coal until about 1960. So in terms of market share then, coal was king for almost 100 years. And so we should be under no illusions that future energy transitions will be any quicker. And we should recognise, of course, that the developing nations are still moving out of wood and into coal as they quickly tear through their own modern-day industrial revolutions. Now, of course, although energy production has been so decarbonising in relative terms, absolute carbon emissions have been rising. In fact, since the Industrial Revolution, growing economies have created prosperity, leading directly to improved human well-being. So the current growth in carbon emissions from nations such as China and India are an indicator that the poor are becoming prosperous. In fact, the great economic divergence of the Industrial Revolution is being replaced by an economic convergence between the stagnating West and the rapidly growing East. And these long historical energy transitions are also one of the reasons behind current interest in shale gas. Since methane has 4 hydrogen atoms for every carbon atom, it's hydrogen-rich, carbon-light and energy-dense. The fact that it's much cleaner than coal is a side benefit that we get from its superior energy density. Globally then, if methane becomes cheap through shale gas extraction, it will help displace coal, as would a growing market share of carbon-free nuclear energy. Moreover, since methane is hydrogen-rich, it's a clean burning fuel that can help alleviate air pollution in the rapidly growing cities of Asia and Africa, and can even be a replacement for oil in transportation. But when it comes to energy density, nuclear fuels beat hydrocarbons hands down. A city powering carbon-free 1 gigawatt nuclear plant only requires about 25 tonnes of fuel per year and a plot of land the size of a modest industrial estate. Again, energy density reaps environmental benefits in terms of impacts on land use and material inputs. Moreover, the city powering plant will produce essentially the same small quantity of spent fuel in solid form, minus the angel share due to relativity. By comparison, a 1 gigawatt coal plant requires approximately 2.5 million tonnes of coal per year, releasing 7.5 million tonnes of carbon dioxide as a gas directly into the atmosphere. Historically, though, we've only scratched the surface of nuclear energy. Pressurised water reactors are perhaps the early Newcomen engines of the nuclear age. And just as the Newcomen engine was eventually outcompeted by the separate steam condenser, so we have yet to see the equivalent of the ubiquitous Watt engine. These will perhaps be high-temperature, fast-spectrum reactors, which can provide a step change in the efficiency through which nuclear fuel is converted into useful energy. And such reactors can consume spent fuel, what we wrongly classify as waste, to generate yet more clean energy. For example, it's estimated that the UK's store of separated plutonium could power the national grid for several hundred years using fast-spectrum reactors, while thorium is seen as a more abundant and superior fuel to uranium by some. So there's no shortage of resources to deliver clean energy into the deep future, but we need the vision and the ambition to exploit it. In considering the utility of energy-dense nuclear fuels, we should also consider that while hydrocarbons represent energy that is not of our time, they represent energy from the sun, stored in compacted organic matter, nuclear fuels represent energy that is not of our place. Their immense energy density comes from the final moments of collapse of ancient stars, which fused lighter elements into uranium and thorium. So our modern prosperity is driven by endowments of compact energy, both from the distant past and from distant space. And as industrial physicist Cesare Marchetti noted, the truly colossal quantities of energy endowed to us in nuclear fuels brings a flavour of eternity, as he put it, to a society worrying that it could be near its limits. So, looking to the future, we should first consider the lessons of history. First, we should recognise that energy transitions are slow affairs. For over 200 years, the now OECD nations have been moving to more energy-dense and carbon-light fuels. But it's clear that we'll still be burning hydrocarbons for quite some time to come. So if we're serious about displacing carbon from energy production, we would do well to accelerate our long historical journey of improving energy density and falling carbon intensity. This will mean, firstly, using far less coal and ultimately less oil, while using more methane and nuclear energy in future. Nuclear is the only means of low-carbon energy production which is both scalable and compact enough to meet the growing demands of rapidly urbanising global cities. Nuclear also provides the constant baseload power that will be needed as the diurnal load cycle flattens, as electricity becomes the energy vector of choice. Indeed, we should remember that the only nations which have been able to rapidly decarbonise their economies are those with a large market share of compact, energy-dense nuclear power. So, for example, while both began their transitions away from oil in the mid-1970s, renewables pioneer Denmark still has per capita emissions far exceeding those of nuclear pioneer France. Now, this is not to argue against modern renewable energy, but for the present, renewables are simply not up to the job of providing socially progressive, low-cost energy and environmentally progressive clean energy on a truly global scale. The problem is one of poor energy density, and so a massive build-out of infrastructure to harvest dilute renewable energy, whether wind, sun or sea, and turn it into concentrated electrical energy. Per unit of energy produced, renewables, such as wind, requires colossal inputs of steel, concrete and land compared to compact, long-lived and high capacity factor thermal plants. And then there's the perennial issue of fitting the square peg of intermittency into the round hole of continuous consumer demand. And this has been evident since the time of James Watt. On a visit by the noted diarist James Boswell to the Bolton Watt factory in 1776, Watt's business partner Bolton remarked, "I sell here, sir, what all the world desires to have, power." Watt and Bolton were not just selling energy, they were indeed selling power, the ability to do mechanical work at a given rate where and when the consumer desires. But more important than carbon in the immediate future is the bottom billion, those who currently live without access to electrical energy in an Elizabethan-era economy burning wood and animal waste with appalling impacts on human health. In fact, this traditional biomass makes up about half of global consumption of renewable energy. So we need to balance the real but uncertain risks from climate change later in the century against the known certainty of the crushing poverty still experienced by so many in the present. And if the bottom billion are to join us in a future of sheer prosperity, then global energy consumption will need to rise sharply in the coming decades. In fact, one of the clearest correlations in economics is the link between per capita energy consumption and per capita GDP. And it's energy and innovation-driven economic growth that generates prosperity, and it's the surplus from that prosperity that delivers value services such as health and education. So let's be absolutely clear. Nurses nurse and teachers teach only because someone or something else is efficiently providing their joules, calories and other material needs. Access to energy is a progressive social leveller. In delivering the modern prosperity that many of us now enjoy, and which even more rightly aspire to, we have largely engineered our own energy economy. While we can be awed by the evolved emergent complexity in nature, the directed walk of the blind watchmaker has often been a poor engineer for human needs. For example, while unthinking biology can evolve wonderful structures manufactured from cellulose and lignin, such as redwood forests, thinking humans can conceive and create metal and ceramic structures, such as the sensational Burj Khalifa, reaching almost 10 times as high. So, as thinking humans, our ideas and innovation have been improving upon nature's often poor productivity, whether modern-day alchemists fissioning atoms or laboratory magicians splicing genes. And while nature processes largely organic materials, human innovation makes use of the full periodic table. For example, a compact, ultra-efficient gas turbine requires some 1/3 of the elements of the entire periodic table, while its air-cooled blades operate in a flow of hot gas at a temperature above the melting point of their constituent metal alloy. The huge temperature gradient between hot gas and cold air ensures high thermodynamic efficiency, in the same manner that the heat engine of the Earth is poised between the hot sun and cold space. So used for electrical energy generation, a compact Brayton cycle gas turbine operating in combined cycle mode will deliver an impressive thermodynamic efficiency of some 60%, about twice that of a Rankine cycle coal plant. And it's the impressive efficiency of modern gas turbines that is one of the reasons for the ascendancy of methane as a fuel of choice. So compare this human-engineered efficiency to photosynthesis in crop plants with an energy conversion efficiency of only 1 to 2%. Nature operates at low temperatures and is limited by the use of largely organic materials. Human innovation can operate at extraordinary temperatures and efficiencies made possible by the use of inorganic metal alloys, ceramics, and other novel materials. Indeed, the growth of efficiency through ideas and innovations has been as much a driver for the human enterprise as the transition between energy resources. Aside from the transition from wood to coal, the Industrial Revolution was also a revolution in efficiency, from the 1% efficient Newcomen steam engine to the 3% efficient Watt engine. Now, while still poor, this was a threefold improvement, allowing the same quantity of mechanical work to be delivered with about a third of the weight of coal. But as Victorian economist Stanley Jevons later pointed out, this improvement in efficiency did not lead to less coal being consumed, it led to more, as improved conversion efficiency drove down costs and so opened up new applications. And indeed, the improvements devised by Watt were eventually superseded by Trevithick's high-pressure steam engine, which increased efficiency and power density to enable the steam locomotive. And much later still, the even more efficient Parsons steam turbine was connected to a dynamo and began for the first time to deliver electricity distributed through a grid. So these extraordinary improvements in the efficiency of energy conversion have continued entirely unabated for almost 300 years. Again, from the 1% efficient Newcomen steam engine to the 60% efficient combined cycle gas turbine. Likewise, the use of clean-burning paraffin fractionated from hydrocarbon oil replaced the traditional whale oil lamp. Edison's electric filament replaced paraffin and was in turn replaced by the gas discharge lamp and now highly efficient solid-state lighting. So each new innovation delivered a step change in energy efficiency. But again, these improvements in efficiency didn't lead to a reduction in energy use, but wonderfully greater energy use, brighter homes and workplaces, and an escape from the diurnal day-night cycle. Indeed, artificial lighting is so important to economic development that it's been measured by satellite and has been used as a proxy for rural GDP. So it's clear then that the end result of innovation-driven efficiency is the mass democratisation of access to energy services. And it's importantly that we don't concern ourselves with the quantity of energy we consume. It's the services that energy provides we desire, whether lighting, communications, or transportation. And with over 1 billion fellow citizens without access to electrical energy, global demand for energy services is far from met. But as we look to the future, for some, the spectacular growth in energy consumption since the Industrial Revolution is but a transient, a one-off binge that will collapse as resource or environmental limits are reached. But we should be careful of these claims. While many worry about peak oil, for example, the Elizabethans deftly navigated the bottleneck of peak wood through the slow transition to energy-dense coal, and in doing so, they helped deliver a society more prosperous than most Elizabethans could perhaps have imagined. But for pessimists, the notion that this growth is almost over is neatly encapsulated in the apparent truism that infinite growth on a finite planet is clearly impossible. So let's test that claim by, again, considering the distant past. It's estimated that just before the advent of agriculture during the Neolithic Revolution, the global population was at most a few million souls. And these distant relatives of all of us should therefore have been the super rich of human history. The entire planet and its resources were at their disposal, shared amongst their small number. In comparison, now that there are 7 billion of us walking the earth, we should be so much worse off, since all that land and all those resources have to be spread so much thinner. But of course, we're now more prosperous than our Neolithic ancestors could possibly have imagined. We have used ideas and energy to multiply the utility of the resources of the finite Earth. And this is where growth pessimists typically stumble, viewing humans as unthinking consumers of resources rather than prolific innovators. Oops. Sorry. Okay, so for example, a small handheld Neolithic granite tool contains atoms of silicon and aluminium, amongst others. And using ideas and energy, we can rearrange those same atoms and add some others to produce a smartphone. Now, of course, it can be argued that the smartphone has significantly greater economic value due to its utility, delivered through the communications, navigation, and the handheld computing services that it can provide. So value has been added to a finite quantity of matter using ideas and energy, and the economy has grown as a result. Again, as with energy, we don't actually care for the quantity of material resources we use, it's the services that they provide that's important. And of course, new resources are created by human innovation. Uranium was once used to colour glass, while silicon was once just sand. We should also consider that by rearranging the atoms of silicon and aluminium in our small stone tool, we've left the thermodynamic entropy of the material largely unchanged. Certainly there's a minimum quantity of energy required to break chemical bonds, some of which will be lost when we rearrange those bonds. But unless we're turning gas into solid matter, for example, the second law of thermodynamics has little to say. If we have a suitable reservoir of high temperature heat, we can in principle rearrange matter into new and more productive forms, while radiating low temperature waste heat to cold space. So the ordering of the human world does not necessarily imply an inevitable disordering of the natural world. Indeed, we should consider that since the Earth formed and cooled, its finite mass hasn't changed. But unthinking biology has evolved immense factories, such as rainforests, which manufacture wonderfully complex structures from dead matter. High temperature heat from the sun is used to photosynthesize dead matter, while low temperature waste heat is radiated to cold space through the forest leaf canopy. And of course, emergent life runs on such gradients. But while unthinking biology taps into flows of energy, thinking humans can use both ideas and energy to rearrange matter into more complex forms. Historically, these ideas have ultimately delivered socially progressive access to services through environmentally progressive dematerialisation. For example, in the late 19th century, the electric telegraph provided communications through subsea cables requiring countless tons of copper and steel and delivering truly atrocious bandwidth. In contrast, though, a modern 6-ton geostationary communication satellite can wirelessly span continents, providing a fire hose of bandwidth for information services. So we have replaced matter with energy as a communications medium, and we've used our ideas to rearrange matter on smaller and smaller length scales to endow it with the extraordinary functionality delivered by modern digital electronics. And this is an exemplar of Buckminster Fuller's ephemeralisation, the ability of innovation to provide so much more with so much less. Through innovation, material and energy inputs for a given service fall, deflating prices and so democratising access to them. The socially and environmentally progressive nature of such innovation growth can be seen in so-called environmental Kuznets curves. These contend that as an economy grows, it pollutes, and, for example, air quality declines. But a turning point is eventually reached at some GDP per capita, after which environmental impacts fall. As an economy grows, it can eventually afford capital-intensive technologies, such as efficient internal combustion engines or catalytic converters, which minimise the inefficiencies of pollution and waste. So it could be expected that this inverted view of the environmental Kuznets curve could hold for carbon. A more efficient economy creates more wealth per unit energy consumed, and so should be better able to sustain the future costs of clean energy. However, compared to the urban smog of the past, carbon dioxide is an inert and odourless gas, and so it does not have the same immediate health impacts as soot or other pollutants, for example. In fact, treating carbon dioxide as a pollutant is in many ways a measure of success, of the quality of the local environment that many of us now enjoy. And the motivation to reduce carbon emissions is therefore through future, not current impacts, and so a Kuznets pathway is perhaps unlikely. So, just as photosynthesizing biology slowly polluted the atmosphere with reactive oxygen in the distant past, thinking humans have weakly modified the composition of the atmosphere in more recent times, an unintended consequence of the spectacular growth of the global energy economy. But unlike organic biology, we can think, innovate, and create. And while unthinking biology slowly evolved the means to deal with reactive oxygen through the evolution of respiration, we will ultimately need to innovate new means of dealing with the metabolism of our own energy economy as it continues to evolve. For example, there's been a sharp growth of interest in geoengineering, defined as active human intervention in the climate system, either to deal with high climate sensitivity or continuing growth of carbon emissions unabated. And initial concepts for geoengineering have centred on scattering a small fraction of sunlight incident on the Earth's atmosphere back to cold space through the deposition of aerosol particles in the stratosphere, delicately engineering the thermodynamics of the Earth's heat balance. Other concepts envisage directly sequestering carbon dioxide from the atmosphere by various means. For example, carbon could be sequestered into biomass by engineering unproductive desert land and stimulating the green bloom of agriculture, or by fertilising unproductive ocean zones to promote plankton growth. And while unthinking biology evolved the means to deal with reactive oxygen through respiration, so in future human innovation may deal with the metabolism of our energy economy through enhancing the respiration of the earth. Indeed, greening deserts, perhaps by engineering the subtle tipping point behaviour of desert land between dry and wet states, may have much wider implications. Innovation on such scales could not only soak up carbon, but transform our outlook for agriculture and so the notional carrying capacity of the earth. Importantly, it would also add to the planetary stock of free energy, that which is available for useful work, such as driving atmospheric circulation, the water cycle, or growing biomass. And as Earth scientist Axel Clyden notes, it would seem that it is only through the large-scale use of human technology that the Earth system could generate more free energy, yielding a more prosperous and empowered planet. So, rather than a zero-sum game where growing human activity appropriates more of a fixed planetary free energy budget, thus leaving less for nature, human innovation can inflate the free energy budget, for example, by greening deserts through photosynthesizing agriculture and pasture and forest. And while we could be rightly concerned about the upsetting nature's equilibrium, let's be clear, there is no delicate balance of nature. The Earth is a dynamic system that is in a far from equilibrium state. Colossal flows of matter transport heat from the equator to the poles in ocean conveyors and in turbulent weather systems, creating wonderfully complex structures. The moon is in equilibrium and it's dead. So one of the key characteristics of far from equilibrium systems is their unpredictability, their adaptability, and their sheer richness. And this is what makes the enterprise of life on Earth in all its forms, from the natural world to human society, so colourful and compelling. We need to clearly acknowledge that the human enterprise is now an integral part of this far from equilibrium system, whether through our energy economy, the growing complexity of our ideas, or the precision and the scale through which we now use energy to rearrange matter into more productive forms. And let's be clear, there is no Mother Nature. If there were, she would as soon see us dead as alive. The human enterprise, self-organised from dead matter, clawed its way from the mud and adapted to ice ages and other natural calamities of a far from equilibrium world. And again, we should remember that the success of human innovation has been in transcending boundaries, whether overcoming the photosynthetic limit of diffused biomass in the Elizabethan era, or even the centuries-long macroengineering of the inventive Dutch, who literally created one of the most prosperous nations on earth, but with a quarter of its landmass below sea level. So climate change and geoengineering are perhaps two faces of the same coin, and our responses to them bring competing views of the future into sharp focus. We can live forever within planetary boundaries set by nature, or we can continue to transcend boundaries and flourish into the deep future. The contemporary interest in geoengineering could therefore provide a platform for long-term thinking to continue the historical success of the human enterprise. In fact, modest interventions in the terrestrial climate through geoengineering later in the century could ultimately provide a platform for thinking on even larger length scales and even longer time scales. For example, so-called terraforming, literally earth shaping, is seen as a means of actively engineering the atmosphere of entire planets, making them slowly more habitable. This speculative and entirely outlandish idea gained a little more credibility by appearing in the respectable journal Nature in 1991. So, as our understanding of the Earth system improves, and later in the century, if we need to deploy geoengineering to clip the edge from the impacts of human-driven climate change, we may in fact set the scene for some truly impressive feats of macroengineering in the far future, whether greening deserts or greening Mars, or protecting the Earth from the natural calamities of the past. Indeed, in the past, unthinking nature stumbled from one catastrophe to another, whether through ice age or even asteroid impact. But the advent of thinking humans offers the prospect of innovation on a planetary scale, whether discreetly cooling the Earth in the near term, or indeed gently warming it in the far future as cycles of glaciation come and go. So perhaps James Lovelock is correct, and the Earth does in fact provide feedback loops to ensure the long-term sustainability of life. But in future, there are likely to be active feedbacks engineered through thinking humans, not just the passive feedbacks of unthinking biology. And even now, human innovation can mitigate the risks from some of these natural catastrophes. For example, by modest tweaks to the orbits of small near-Earth asteroids, either to avoid future impacts or just perhaps to shepherd and capture them for future resource use. And as physicist Freeman Dyson notes, it's thinking humans that have an intrinsic duty, as he states, to carefully reconstruct nature so that humans and the biosphere can both survive and prosper. Finally, if we consider the largest of length scales and the longest of time scales, we should note that one of the most remarkable but unremarked findings of modern science is that the wider cosmos is silent. Future telescopes will be able to detect oxygen and other indicators of far from equilibrium life in the atmospheres of planets about distant stars. However, for the present at least, the stars appear to be dead, and there are certainly no large-scale structures such as star-encompassing Dyson spheres, giant artificial heat engines with a suspicious excess of cool photons being radiated to cold space, or even low-bandwidth radio chatter. This great silence may simply be an artefact of our lack of imagination in guessing what to look for. Or it may be that only thinking humans have self-organised from the curiously low entropy state of the early universe. And as thinking humans, we've woken up from dead matter to self-organised conscious life, only to find ourselves alone in a dark and apparently empty room. And if this is indeed the case, we are, all of us, more precious and exquisitely unique than we can possibly imagine. So Fermi's great silence should therefore not be daunting or unnerving, but life-affirming. And it should motivate us to look beyond the parochialism of the present and see a clear purpose and direction for historical travel. So thinking humans can now use ideas and energy to reach out and touch the surface of other worlds, using for a short duration the energy of nations to lift people and machines out of the Earth's gravity well. And if, in the deep future, we ever accelerate machines of our own making to drift at relativistic speeds, ghost-like between the stars, we will literally require astronomical quantities of energy. And of course, the wider universe itself is in a far from equilibrium state. When we look at the night sky, we see cold space filled with dense, bright stars. And while it's quipped that in the heat death of Lord Kelvin's entropic universe, the doomsters will always be right, the human enterprise is just in the first flourishes of youth. There is a wealth of matter and low-energy entropy available to us, and a near eternity in which to do good with it. So the sometimes misanthropic hues of contemporary thinking see humanity as turning nature into dead matter, but looking into the deep future, it could well be that it's humanity that turns the dead matter of a cold and dark cosmos into conscious thinking life. Professor Arbuthnot, ladies and gentlemen, thank you for your kind attention, and it's been a true honour to deliver my lecture to you this evening. Thank you.
Checking. Well, Colin, we do not have an infinite time to discuss the significance of this, but that was a fascinating journey from the origins of the Earth to what might happen in who knows how long a time. So we're at the question time now. Who would like to begin? Just hold up your hand and we'll get a microphone to you.
Catherine Smith, thank you very much for that tremendous look at the long-term future of science. Now, one of the phrases you used was that equilibrium is death, as equilibrium of the moon means that it is dead. Now, there is such a thing as the concept of dynamic equilibrium, and the danger is that in our hubris, since we can't even get tampering with economics right, that in tampering with geosystems, we might destabilize the dynamic equilibrium rather too severely and not be there to pick up the pieces. Can you advise on how, in your scenario, we manage that only those who have thought things through properly get to tamper with the geosystem?
Yes, I would entirely agree with your statement. In terms of the moon being dead, I mean, the moon is dead in the sense that it's an equilibrium, chemical equilibrium. You know, the Earth is in a far from equilibrium state, both chemically, both in terms of the dynamics of the atmosphere. So you know, we live in this very complex system, which is in a far from equilibrium state. And of course, it's that complexity which gives all the wonder of nature and the complexity of human society, which, you know, us as part of nature. In terms of geoengineering, I mean, this is of course, the crux of the modern debate in geoengineering, is that it is seen as absolute human hubris to imagine that we could tamper with the Earth's far from equilibrium climate system and do it in such a measured way that the outcomes would be guaranteed to be beneficial. And I would, again, I entirely agree with that. But my concern, though, is that the way the debate has gone just now is that we've not even dipped our toe in the water. Even the idea of doing research in geoengineering is seen as human hubris, as something which will divert us from the kind of key tasks of decarbonising the economy and growing its energy efficiency. But you know, that idea of kind of forbidden knowledge actually really worries me. I mean, you know, science is about exploration of knowledge without constraints. So if we were to do research in geoengineering, if we were to start to do field trials of geoengineering, which are people being proposed. So we're, again, not on a global scale, but doing iron fertilisation in the ocean, measuring plankton growth, measuring how much CO2 it soaks up, or depositing sulfate aerosols in the stratosphere on a very small scale, again, to measure the quantity of sunlight reflected back into space, then those aren't dangerous experiments. All we're doing is taking the first steps, the first very small steps, to understanding how potentially we could engineer the Earth's climate in the future. But even that, it's not, we talk about geoengineering, what we're talking about is reducing, for example, for solar radiation management, we're talking about reducing the flux of energy of the Earth by about 1 or 2%. So it's a tweak in the grand scheme of things. It's not a massive intervention. And what I would see, if again talking pragmatically, I don't see any chance that carbon emissions will fall anytime soon, because there's 1 billion people without electricity. There's 2.5 billion people who burn wood indoors for cooking. So globally we have a huge unmet demand for energy services. And that demand is being met just now. We see that in China, we're starting to see it in India, other rapidly growing economies. And that's wonderful, because that prosperity improves people's lives, improves longevity, education, outcomes, health, the life chances of people. So that's been socially progressive. But if we look at the longer term environmental impacts, and if we believe that climate change is an issue, which I do, then we have to square that somehow. And taking initial steps of research in geoengineering, doing some initial field trials, I think is an entirely appropriate way forward. Doesn't mean we would field geoengineering on a large scale in the future. It just means that we're prepared for it and we understand a little bit better about it.
Right. Next question. Yes.
I'd just like to make a comment here on...
Wait for the microphone, Sean.
I'd like to make a comment here about just what Colin said about it pushing new ideas forward and so on. And I'd like to, first of all, I mean, I'm speaking actually as Colin's 25 years ago PhD supervisor. Colin did not need supervised. It was a joy to work with him from the beginning. We had great talks about entropy and all sorts of things back then. Anyway, I would just like to congratulate him on a great talk and so on, receiving the Kelvin medal, and just to say that to encourage people to do really innovative things, and not, even if you disagree with all the conclusions Colin reached, his vision and thinking things through is, I think, wonderful. That might, well, it would have happened anyway because Colin's a different person, but the Royal Society of Edinburgh and the Cormac bequest enabled it. Any head of a physics astronomy department like I was in would have declined, as ours did, to fund Colin to do research into solar light-driven spacecraft, light-sailed spacecraft. No way would anyone allocate a Research Council student funds to do that. Had it not been for the RSE Cormac scholarships, Colin would not have had the chance there when he did. So I think the lesson is, the Research Council's got awfully focused on what they know to be good, but we do need things like RSE funding to enable really bright people with very good ideas like Colin to pursue them. So congratulations to Colin and the RSE for encouraging such work.
Yeah, I think it's good to respond to that. I think having the funding from the RSE for me is absolutely key. And I think that opportunity for young researchers to conduct absolutely unconstrained research without thinking about research impact, which we're all driven to now, is so important, because it's our prosperity for the future and also our impacts in the environment and reducing them. We need a fire hose of ideas from the present. And just now, I fear that we're not getting that because the research councils are so focused on delivering near-term economic impact. Yeah, I should also say, I believe I was the last Robert Cormac Research Fellow because I think I burnt the endowment capital. so thanks and apologies at the same time.
Well, what that means is that burning things is not always self-limiting, Colin. Any other questions? Can I ask you, I mean, over the course of your lecture, you went through phases of how we have used energy in different ways, how societies have used energy in different ways, how massive amounts of carbon dioxide and carbon generally were produced by wood burning and coal burning, and then you took us through how that efficiency was increased incredibly. Given the balance of what is happening across the world in general, Are you optimistic or pessimistic about climate change?
It's a difficult question. I think the way we've been coming at it for the past 20 years, I think it's been completely wrong.
Totally wrong.
It's been totally wrong. In that we've seen, for example, fossil fuels as uniformly bad, but of course there's a spectrum of fossil fuels from coal through oil to methane. Methane being hydrogen rich in carbon light. I mean, one of the ironies of the kind of international discussion on climate change over the past 20 years or more is that the one country which has actually decarbonised in the past few years has been America, who didn't sign up to Kyoto. And they've done that by using shale gas to displace coal. So,
could you just interrupt? To what extent has shale gas had that effect?
I think it's a fairly significant effect. I mean, I can't give you the numbers, but certainly the cost of natural gas in the US has plummeted. And because of that, it's cheaper to burn gas than it is to burn coal. Again, one of the ironies is that hydraulic fracturing for shale gas is seen by many as almost some kind of intrinsic evil. But in fact, it's one of the most progressive things we could do for the environment is reducing the cost of gas, reducing the cost of methane, because if we do that, then it displaces coal. So in terms of, if we're at all worried about carbon emissions and carbon through the rest of the 21st century, coal is what we need, is what we want to eliminate, not gas. We want to be using gas and nuclear to replace coal.
Okay. Yes, in the centre and then in the front. First in the centre. Thank you.
Well, I'd just like to comment on what was said actually by the speaker over here about research. It's very important that we have some organisations that are allowed to do blue sky research with no constraints whatsoever. I used to work for a company, actually Xerox, in fact, and out of Xerox came the internet, came Ethernet, came the graphical user interface, all the things that we now have in modern computers, and that was caused by a bunch of guys, and I've seen them, sitting at their desks with their feet on their desks, hands behind their heads, thinking, and every so often somebody came up with a really good idea, and that's just a few of them.
I think we would probably both agree with that.
Yes, no, absolutely, yeah. Although I think if my principal, Sir Jim McDonald, had to come around and see me with my feet on my desk, I'd be getting my P45 for not working hard enough. As you know, as a former principal of Strathclyde University.
Tell him to give me a ring. Next one, yes.
Thank you very much, Colin. John Baxter from BP. Thank you for a fascinating lecture. My career has been 30 years nuclear, then electricity, now in the oil industry. So it's not a technical question I'm going to ask you, actually, because I've been musing as I've been listening to you, and all of the things you're saying we should be looking at, I agree entirely. But the world's gone against us on genetic mutation. The world's gone against us on plutonium. Why? Because I think as scientists and engineers, are we really good at explaining what we're doing to the general public? And I think actually as we get more complex on things, there's something about how do we actually just help people to understand, because they don't trust the financiers. I don't think they trust the scientists. I don't think they trust the politicians. And when I was running Doonray, the advice was, can you convince your grandmother in the corner of the room when you're talking about a topic? And maybe we've just kind of stepped away from how we help people to understand. So can you help me there with that? Because I'm trying to help people understand shale gas, and other issues that we have in our industry. I'm
not sure I can help you directly, but I can certainly empathise. An example of that, there's a documentary film called Pandora's Promise. You may have seen it or heard of it. It's a documentary about nuclear energy, and I think it's on at the GFT in Glasgow fairly soon. And it's a wonderful film, and what it does, it addresses nuclear energy, but not from a scientific viewpoint. It's from an emotional viewpoint. And in fact, one of the people in the film, Mark McInnes, who's an environmental activist for many years, who went from anti to pro-nuclear. And I spoke to Mark about this, and he says this: the issue is that as scientists and engineers, we can put things into numbers, and we can talk about risk, radiation doses, we can talk about energy density. But for the wider public who may not have a scientific background or interest in science, they deal with things like nuclear energy on a purely an emotional basis. it's almost kind of visceral fear of the unknown, and it's tremendously difficult to get over that. And I've found that is you can't convince somebody by numbers. Maybe using analogies is a way to do it, or using counter examples. I mean, the shale gas one I think is almost perfect in that. If we point to who's actually currently reducing CO2 emissions, what's the Americans? The country that didn't sign up to Kyoto, they're actually delivering because they're starting to swap out coal and methane. So I think maybe it's just getting down to the practical, nailing down really practical examples. Or again, the example where the carbon emissions per capita of Denmark are still way above France. Or another one, which somebody made the point the other day that if Germany reaches its goal of 80% low carbon energy by 2050, they'll be over 60 years behind the French. So I think maybe pointing out these very tangible examples is maybe the way to go to it. But I agree, certainly not to use numbers, to stay away from numbers.
One of the things that the Royal Society of Edinburgh does, as some people here will know, is picking up some of the points that have been made, is that we do try to convey modern ideas and what has happened during scientific progress, both in physics, biology, and all the rest of it, to young people. And you have to actually use a language that they can understand and become enthused about, because if they don't become enthused, they won't want to do the subject, and they switch off because they think that science is too complicated. So there is an issue about communication here and about the way in which we describe things.
Yeah. An example, the slide I had, I think, was of Torness. So down the coast in Torness, a 1,000 megawatt nuclear plant, producing energy essentially 24/7 on a plot of land about the size of a modest industrial estate, and that produces more energy in a year than every wind farm in Scotland combined. Now that's a simple way of trying to explain the benefits of energy dense, high capacity factor, long-lived thermal nuclear plants. It's just through these very simple examples.
Yes, a question on my right, just halfway up.
Jane Bauer, is anybody in the UK doing work on thorium now?
I believe there is. There was a group of. There was a small group of university of physicists from, I think, Cambridge. I can't remember, a couple of other universities, maybe Manchester, who got some funding from EPSRC to look at the use of thorium for nuclear fuel. And they were looking at, it was an accelerator-driven form of using thorium, where you use a particle beam to create a spray of neutrons, and then you use that to generate energy from thorium. So there is some work going on in thorium. Again, that's what about shale gas? It's a very interesting area as well, in that there's a lot of proponents of thorium who view it as a superior fuel to uranium. Both in terms of the residual, very small quantity of residual waste you produce, the inherent safety of some forms of using thorium. But I guess there's a lot of capital, both money and time and effort being put into uranium as a nuclear fuel. And so the way of using thorium, some of them are just so different than the way of using uranium. There's probably a new industry which would emerge around thorium in future. It's not something which the current nuclear industry would swap from one to the other.
We're going to take two more questions, one on the left and one at the back. Yes.
Is it worth spending money on research into fusion power?
Again, it's a very interesting question. I think fusion is one of those, for my very much outsider's understanding of it, it's one of those technologies, one of those ventures which has and will take many years to come to fruition. I think if you look at one statistic I did come across is if you look at the fusion triple product, which is a measure of how good your fusion system is, the fusion triple product has increased faster than Moore's law over the past 30 odd years. It's still not at break-even, but it's actually the improvements have actually been very substantial over the past few decades. I think will be very interesting to see what happens with the ITER nuclear plant fusion plant in France, and when that's eventually completed, and they do some of the experiments on the plasma torus. But yeah, it's something which is, I guess it's not there yet, maybe in the future, but it's certainly worth investing in for the long term.
And one at the back had their hand up. Yes.
Just on the topic of communicating this to younger people, and not that I'm trying to say anything by it, but having looked around, I think I'm one of the youngest people here. I'm actually a student at Strathclyde doing mechanical engineering, so I'm finishing my master's this year. On a sort of local scale, regarding Scotland's own human enterprise, and feel entirely free to not answer this question if you feel like it. What do you feel the vote for or against independence could have as an impact on our own human enterprise?
That's a different kind of fusion.
Yes.
True. As I say, if you feel free not to answer.
If I can avoid answering the question directly, and if you excuse me for not being flippant, but I didn't read all 263 pages of the white paper, but I did flick through it, and I did a quick search of the questions and answers at the back. The one thing I did notice, it said that Scotland would have access to space through the UK Space Agency down south. So for me, as a space engineer, if you like, it would probably be not much changing, since I don't think we'll have a Scottish Space Agency for independent. I think we'll continue to collaborate with the UK Space Agency. So if that's definitely avoided your question.
But we are going to soon launch our first satellite. Tell us about that.
Yes, there's Clyde Space, which is a Glasgow-based company for 25 engineers, the West of Scotland Science Park on Maryhill Road. And they have built and have delivered UCube-1, which is a CubeSat, it's a little 3-kilogram microsatellite. And that was developed through UK Space Agency funding and through a knowledge transfer partnership we had between Strathclyde University and Clyde Space. That's been a hugely exciting project. UCube-1 has been delivered to the UK Space Agency, or the customer, and I think is either just about to go to or is in Kazakhstan, and will be launched in spring of 2014. And even though it's a British-funded satellite, it's Scotland's first built satellite, so there's a kind of Andy Murray of space here of how we deal with UCube-1.
That's an appropriate point to ask for a vote of thanks. Thank you very much.
Sir John, ladies and gentlemen, whenever I see that Britain's Got Talent is on again, I think to myself, Britain doesn't need talent, it needs genius. But what is the difference between the two? To my mind, talent is appreciated ability. It is expertise that we enjoy seeing, hearing, reading, or otherwise sensing in others. Genius, on the other hand, is not about consensus recognition. It is about challenging us and our preconceptions, about speaking the truth as the person sees it. Genius demands a response. Tonight, Colin has situated the ever-current debate on science and society within a spectrum of human technological development that reaches not just from the past, but also into the future. His message is one of optimism, which we should set against the prevailing pessimism about the human and planetary future. He has sounded a clarion call for us to rethink our relationship to the planet as its shepherds, not its helpless slaves. In doing so, he is discharging the responsibility of the engineer to engage with and challenge society as much as to develop ideas and technologies for society's future. That Colin embraces this responsibility is one of the many reasons I was proud to nominate him for the Lord Kelvin Prize. The 18th century German scientist Georg Lichtenberg said, "Everyone is a genius at least once a year. The real geniuses simply have their bright ideas closer together." It is the imaginative leap characteristic of a moment of genius that Colin McInnes has shown us this evening, and I hope that we will all respond to it. Let us thank him again for his talk. Thank you.
Thank you all for